savings that are both benefits in environmental terms and energy security terms, and it saves you dollars that you can spend on other things. All right? So that's the basic idea here. So everybody here knows what an externality is. Look at this. What a cool picture. I've just learned how to do animations. I'm pretty proud of myself, but again, I'm late to this game. So the basic idea, as we all know, right, if the private marginal cost of vehicle weight, let's just bring a vehicle down to one dimension. We'll ignore whether it has GPS or anything like it. Let's just use vehicle weight as the characteristic we care about. And we have the dollar per mile, which is the price of operating that vehicle on the y-axis. If the marginal benefit, right, of driving a heavier vehicle is positive, meaning you like heavier vehicles, right, they give you more safety benefits and more comfort and other things we really like. You sit higher and you can see Alcatraz even at the old span of the Bay Bridge. And we look at the private marginal cost of vehicle weights. The equilibrium vehicle weight we would get if we ignore the externalities would be W star and P star. However, if there's externalities that we cause from that additional vehicle weight in terms of fatalities, what you get is the social marginal cost is higher than the private marginal cost, and this is the classic externality picture, that the socially efficient level should be W double star, that's annoying, and P W star. So price would be higher, and the weight would be lower. Of course, this here is the optimal tax, right? It's the external cost at the optimal level. But this is old EAP 100 stuff. Okay, so how do you go from deaths to dollars? Ooh. Anybody here taking ethics classes? Really? In high school? Everybody should take some sort of ethics class at some point. It's good for you. It'll make you think about what you think about. But the point here is, so in economics, we do this a lot, right? We have to put a dollar value on human lives. If we do a benefit cost analysis and we figure out what the benefits from better air are, we need to figure out how many fewer people die from bad air. And then in order to compare this to the costs of improving the air, we've got to turn these deaths into dollars. This is called the value of a statistical life. This turns a statistical life into dollar amounts. The Department of Transportation uses $5.8 million 2008, which is about $6.2 million in today's terms. So your life, in the government's view, is worth about $6 million. How do you figure out what the value of statistical life is? Ask Mike. I'm sure he'll talk about it. But basically, the idea in the early literature was to look across jobs, right? Each job has a different risk level of dying associated with it. Being a college professor is pretty safe. Being employed in agriculture and working on fields and working with combines is one of the most dangerous jobs in America. People get injured and killed all the time. So what you do is you look at hourly wage rates across different professions, and you look at what the variation in wages is as a function of the risk of death on the right-hand side. So you use an econometric equation. You look at wage as a function of the risk of death from the job, plus a whole bunch of other things, meaning average level of education required and so on. And then you look at the coefficient on probability of death that tells you, for a 1 unit increase in the probability of death, how much more in wages are you expecting to be paid in order to accept that higher probability of dying. Then you take that number and you ramp the probability up to 1, and that gives you a dollar amount, meaning how much would you be willing to accept for death with certainty. Sounds pretty crazy, doesn't it? See, you're laughing. I had the same reaction first time I heard it. I've just seen it so many times that I don't laugh anymore because it strikes me as strange. But that's the numbers we use, right? And there's all kinds of cool papers. There's people using these reality TV show things, Alaskan fishermen, the ice truckers across Alaska, and trying to figure out what the value of statistical life is. But it's somewhere between $3 and $10 million. Now, if God forbid you're in an accident and the other person dies, that family could theoretically, according to an economist, sue you for $6 million. I assume that nobody, or very few of you, have assets of that magnitude that you could just pay, right? So when we are held liable for an action, right, we're expected to either have the assets to pay for it ourselves or what? Insurance says it right on the slide, right? Liability insurance. So when you get car insurance, you have to have liability insurance. If you injure somebody else or you kill them, the insurance pays some sort of monetary award to the other person. So you pay probably $100, $150 a month in insurance to get that. Well, most states require $25,000 or less in liability coverage. Some states don't have any liability coverage. But the most anybody's going to get, right, my liability coverage, because I'm risk averse, is somewhere near $300,000. I would never get liability coverage for $6 million. So one way you could argue we solve this issue is simply have people get liability coverage that amounts to that exact amount of $6 million or something like that. We could talk about it. It's an interesting idea, but it would mean completely redoing the insurance scheme in the United States and requiring people to get 46, more than 100 times the level of liability insurance they get now. Now, the thing you want to ask yourself, and this is something we're really big on in social sciences now, not now, we've always been, we've just never had, not until recently had a good way to get at that, is what's the ideal experiment you'd want to run if you wanted to learn about the effect of vehicle weight on the probability of fatalities, right? If you're in physics, you can control the experimental environment, except for the factor you're interested in understanding. You can hold the world still. In economics, that's impossible. We have 7 billion people running around the planet, making hundreds of thousands of decisions each day, which depend on other people's actions, their own action, external changes in nature, and so on. So the world never holds still. But if I could run the idealized experiment in my world, what I would do is I'd take about 50,000 of you, and I'd take 50,000 cars, and I'd randomly assign these 50,000 cars across individuals, right? That means there's no selection. Riskier drivers more likely having received a heavier car. You randomly get assigned a car of a weight, and I let you drive around for a long time, and then I record the fatality rates and look at those as a function of vehicle weight. I can't run that. The National Science Foundation, I tried, but they won't let me buy 125,000 cars because I need good cars and bad cars. I need all kinds of things here. So they won't do that. So I can't run that experiment. So the real world we're faced with is one where vehicles aren't randomly assigned. You choose the vehicle, right? My sister, even though she has 2 kids and 2 strollers, refuses to let go of her Mini, right? So she has a Mini Cooper. The thing's ridiculously small with 2 kids and 2 strollers, and she makes it happen. So people select cars they like, that fit your image, that fit your lifestyle. We don't really know, but the one thing we know for sure is that vehicles aren't randomly assigned, and the worst part is we don't know what vehicles people own. DMV data is highly confidential. There's only 1 or 2 researchers in the world that have access to DMV data who actually know who drives what car, right? In theory, and that's still imperfectly measured. So what we've got is something very imperfect. We've got data on a bunch of accidents, and we're going to look at, conditional on being in an accident, what's the probability of a fatality as a function of vehicle weight in the other vehicle. So pretty cool. I'm going to spare you this. Well, maybe I won't. I just want to make it clear. This paper is about vehicle weight, all right? And we can do a really good job at nailing down the impacts of vehicle weight. There's a bunch of papers who like to point fingers fingers at SUVs, saying SUVs are the source of all evil. I'm going to show you some evidence that's consistent with SUVs having an additional penalty in terms of just their vehicle weight, because they have higher bumper heights. The way the momentum hits you when you get hit in a lower car is more likely at chest height than at your feet. So there are some characteristics of SUVs that make it possible that they're even worse. But this is not an SUV paper. This is a pure vehicle weight paper. Heavier vehicles are worse to be hit by than lighter vehicles. Heavier and SUV is even worse than just heavier, but we can't nail down that effect very well. So I've answered this question already, but we'll put those slides on whatever fancy new technology the university has decided that you should be using for course websites now. I'm sure it's working flawlessly and you have no problems whatsoever. But the point here is this is accident data that a police reported. I don't know what happens if you drive your car into a tree and then drag it home and never report it to the police. So if it's not reported to the police, I don't know. Blah, blah, blah. I've talked about this. Boring. Let me talk about the cars a little bit. So if you're looking at the mean weight of the vehicle in our data set that we could really conclusively nail down the right vehicle, the average weight is 3,051 pounds. That's a little bit lighter than a 3 Series BMW. There's about 17.5% light trucks. The average year is 1992. There's about 1.5 people per vehicle. The average fatality rate is about 0.19%, and the average serious injury rate in an accident is 3%. So there's a 3% chance, conditional on being in an accident, that somebody will be seriously injured in a car. There's about a 0.2% chance that somebody's going to die in a car accident. So let's cut through the chase here. I wave my Harry Potter wand, fancy econometrics, years of computer code, daisy chain Macintoshes, Max and Mike writing computer code, mostly Mike. And out comes this nice table here. What this table here says is vehicle 1 weight. This is the striking vehicle weight. And what we're seeing here in a bunch of different ways of specifying the econometric model is that having a 1,000-pound heavier vehicle hit you increases the probability of somebody dying in that vehicle by roughly 50%, right? Ranges from about 39% to 53%. How are these models different? So this addresses your point in the corner there who had just walked out, but you came back just in time. Here we just control for what's here, meaning vehicle weights and whether the vehicle is a light truck or not. Here we also control for weather, meaning how bad was the weather that day, geography, where did it happen, and driver characteristics. Plus here we do allow for city fixed effects, which takes out the impact, are you in a rural setting or not, and see whether the people were wearing a seatbelt. So no matter what you control for, that effect is really robust. It goes up by about 50%, the risk of a fatality. Let me just point something else out. Vehicle 2 weight, this is the impact of, or the benefit of sitting in a heavier vehicle when you're being struck. Come on, Max. Struck. It's negative, right? That means being in a heavier vehicle decreases the probability of dying in a car. This just means you sitting in a heavier vehicle makes you better off, right? That coefficient here, let's look at the last column here, is almost the exact same size as the one on the external cost, right? So there's a perfect trade-off here. So if you decrease the vehicle weight of both vehicles by 1,000 pounds, the change of the fatality, the probability of fatality overall in that 2-vehicle accident doesn't change. Okay, what other fun things do I have? Where am I? That's boring. That's not so boring. How about serious injuries? Those are a little bit more troublesome. But again, what you're seeing here, same regressions. The external cost of an additional 1,000 pounds on serious injuries is about 20% increase over baseline. But the private benefits of vehicle weight on the private probability of a fatality right here, again, the opposite sign, but slightly bigger than the external costs here. But again, there's this nice trade-off right here. How much time do I have? 2:30? 3:30? I like hearing myself talk. All right, that's terrible. So we could sit here for hours and talk about this, but I have exactly 6 minutes left and about 30 slides. So let me pick the ones I really want you to think about. But I think what I've hopefully said now, that there's an external cost to being hit by a heavier vehicle and a private safety benefits. We do a crazy, crazy detailed job in this paper of worrying about reckless drivers selecting into heavier vehicles, and we show that doesn't affect the results. And we also do a big effort at looking at which accidents are in the data and which aren't to really figure out whether our sample selection here gets us issues. Bunch of falsification tests. It stands up, all right? Now, how would you want to regulate this? So if you think about this for 2 seconds, what you get is you should charge the individual driver a tax on the externality. But what does the externality here depend upon? Starts with W and ends with 8. All right? The size of the externality depends on how heavy your vehicle is. So the optimal tax here depends on how heavy your vehicle is. So that means not everybody should pay the same per gallon, right, or per mile, but people who drive heavier cars should have a higher tax rate than people who drive lighter cars. Question? VSL is the value of a statistical life. Yeah. So you can ignore this. I'm just giving you the slide so you can read through those later, but I'm just going to give you the intuition here, pretty straightforward. So this means per mile, a heavier car should pay a higher tax than a lighter car. Well, let's think about this for a second. If we put a tax on the price of gasoline, do heavier cars pay implicitly a higher tax per mile than lighter cars? Why is that? Exactly right, right? So implicitly what's happening is because you have a heavier car, the car is less fuel efficient and it uses more gallons of gas to drive that mile. So if you tax gas, that sort of mimics the optimal policy here, which is a weight-specific per mile tax. And that, I think, was the insight where we got giggly. We were like, this is awesome. We got really nerdy, drinking our green tea. This is the only time this year I'm wearing a suit. I'm invited at the Chancellor's house this evening for a reception, so this is as fancy as it gets. Usually it's green tea and shorts. But the point here is what a gas tax does is it mimics, and all the details are in here, it mimics the effect of this weight proportional optimal tax quite nicely. So for all vehicles in our database for which we have miles per gallon and weight, we calculate the optimal weight-specific tax, which is the right way of doing it, and then we look at what the gas tax, if you just put a 10 cents or 40 cent or $2 gas tax onto each gallon of gas, how similar are they, right? If they were perfectly similar, they would line up right at the 45-degree line. They don't line up right at the 45-degree line, but it really does look like a nice data cloud along a 45-degree line. This is a so-called sunflower plot where the more petals you have on these, the more observations are there. They're very cool scatter plots. But the point here is that for 71% of the vehicles in our database, the two taxes are within 1 cent per mile, which is really in the noise, and 97% are within 2 cents per mile. So what we're arguing here is that a gas tax is a pretty good proxy for whatever the optimal vehicle weight tax would be here. So they're not very different. Now, I'm going to leave you and let you go have a nice lunch, but my last 2 minutes here are pretty simple. Now, until now, we've looked at vehicle weight as a good thing, right, because it makes people safer. But we're arguing here it actually makes others on the road less safe. Now, the depressing part of this is if you fix the problem with a $1.20 or $2 gas tax, the details are in the paper, you're going to get a lighter vehicle fleet and you're going to get the same number of fatalities. So awesome, Max. Everybody pays $2 more for gas and we get the same number of dead people. It's true. What you do get also is you get a much lower consumption of tires, right? Much lower consumption of gas, higher energy security, less climate change, and all the other benefits we get from reduced oil consumption. Now, how optimistic am I that this is a viable policy proposal? The easiest way to not get elected into office, use the word gas tax just once in your campaign, right? You're not going to get elected. But what this does is it points out this issue that vehicle weight has this big externality and it's a bad thing. So this is the day we finished this paper. I had this favorite record store in a basement on Green Street, and there's an Italian bakery right outside. So, the point here is you want to be in this car, not in this car right here when you get hit. So there's now a bunch of follow-up work here that looks not only at the average weight of the vehicle fleet, but that looks at dispersion in weights in the vehicle fleet. So maybe we shouldn't have the distribution of weights be so extreme that you have a Hummer versus a Fiat, but squish them closer together. So thank you for listening to my bad jokes. You got half the lecture on tape. Mike can answer lots of questions about this paper, and he'll be back on Thursday. All right? Thanks.